Very good morning. Today we are going to see upgradation on this particular course. So till last class what we have seen what is transformation matrix, why we need a robot kinematics, and what is the issue will come with the composite rotation. So in this particular class we are going to see about the kinematic parameters or kinematic parameters, why these kinematic parameters are important that we will be seeing. So before that, just giving a very brief introduction. For example, I have two bodies. There is a information you can say available with respect to one body. Can I transfer these information to another body? If this is the case, so how we will do it? So in that sense, there are several representations or several notations have come. So we are going to see one of the best one, or you can say one of the best to address this. That is what we are going to see. Okay, so in that sense we will come back with the regular aspect. You can see that the disclaimer or the warning or the note as common. So this particular course or lecture is actually like prepared wide range of resources. In fact, this course or this particular lecture is not used external resources. Still I am using the standard you can say protocol. So now we can see that this particular lecture, which is we call lecture 5. So we will be talking about kinematic parameters. In that sense, I will be talking about why kinematic parameters and how that would be beneficial. In that one particular approach we are going to see. In that approach, we would be seeing two, you can say sub-classification of kinematic parameters. So these are we are going to see. So let us start the particular course with a very general way. So you can see that when you want to know the information between two bodies, what are the prerequisites? The first prerequisite is actually like you have to, you can say choose particular coordinate frame. We all agree that this particular course, we initially itself we said that we are going to follow the Cartesian coordinate frame or Cartesian coordinate system. So we can see like easily we can fix the three axes as a coordinate frame, three unit vector mutually or orthogonally arranged. But there is a choice. Okay, choice of you can say locating those frames. So immediately one will say that sir, we are talking about body, then the centra or you can say centroid or center of gravity is the easiest choice. Yes, I agree. So if we fix it the center to center or you can say center of gravity to another center of gravity, how many variables required to describe the body transformation one to another? So we all know, right? It is actually like in space. So obviously you can see that the number of parameters to describe the information between two frames are required is 6. So which is actually like 3 translation and 3 orientational parameter. This 3 orientational parameter we got it from the composite rotation matrix, and this 3 translation parameter we got it as a simple position vector. We all agree, right? But you know, like one body is actually like constrained with another body. That is what we call joint. But if I use or if I choose a choice of coordinate frame which is associated with the center of gravity, I may not be using the constraint, right? For example, I take these are the two body. Okay, so this is one body and this is another body I can take. So now this is constrained on this particular you can say joint, right? So now this joint is actually like nowhere fixed. For example, I am putting a center of gravity as my frame reference. So this is one body reference and this is actually like another body reference. But this to this, definitely I required actually like 6 parameter. However, if I actually like bring this constraint, can I use it anything beneficial? So this is what one of the bigger question which will come into our mind. So that is what we are actually like trying to see. Can we use the constraint, which is nothing but joints? Can we use the joints and their location as the frame reference? Or you can say fixing the coordinate frame or you call the body frame. Yes. So that actually like one additional benefit that we are going to see in the upcoming slides. So now we will actually like make it very general. So if I talk n degree of freedom spatial linkage, that too like a serial manipulator. So then how many frames are required? So you know like n degree of freedom means actually like it would be associated with at least n plus 1 body because the ground also one additional body. So that is the case. So then you have actually like n plus 1 frames are required. In addition to that, this is what I assume that the end effector or you can say the end point where the operating is happening. So I need to actually like associate it with one frame this. So in the sense you can see that if you have n degrees of freedom spatial linkage or serial manipulator, then you should have at least n plus 2 frames. So then how many variables required to describe this particular system? You can see like already you know each you can say body to body transformation, you need you can say 6, right? So now you have n plus 2 frames. So obviously you would be coming with, you can say 6 into n plus 2, you call parameters to describe, right? So when you talk about describing the entire system and its arrangement, then you can see that there are actually like 6 into n plus 2 parameters required. So can I actually like reduce this? This is one of the question. Can I reduce this? Obviously we cannot reduce, but what we can do, we can approach or we can incline to some kind of arrangement, or we say that this is what the body arrangement, then we can definitely try to, you can say, minimize the number of independent variables. That is what our interest. Okay. So then this is one focus. Then what the other focus, you all know, we have studied or we have gone through the composite rotation. So the composite rotation itself, there are several ways to, you call, represent, right? So one we have seen Winkel angle, the other one we have seen Cardan angle. There are other Euler angle or Euler approaches are there. So in the sense, there is no unique way. And further thing is actually like the orientational parameters are not straightforward described, right? It is actually like described in the form of matrices. Even you go screw transformation, still the final end you have to represent in terms of matrices. So in the sense, what the bigger, you can say, setbacks coming here. So there is no straightforward technique to mention orientation of each frame. So if these are the cases, okay, so one is actually like you have, you can say, large pool of parameter. The second thing is there is no straightforward technique to mention the orientation of each frame. So then can we have some kind of, you can say, additional benefit, or can we have some approach which will make you can say simplification of this representation? Yes, there are several attempts made, and in that one of the popular attempt, what we are going to take it in this particular course called the Danawit-Hartenberg approach, we simply call DH approach. So there are actually like two researchers called Jacques, or you can say Jacques Danawit and Richard Hartenberg. They actually like introduced this convention in 1955 in order to standardize the coordinate frames for a spatial linkage, that to serial spatial linkage. So this is what the, you can say, starting point. But what they did not actually like reduce anything. But what they did, they actually said that if you have in certain way of the representation or certain way of the, you can say, link to link arrangement, then we can represent the entire, you call, frame to frame information with only 4 parameters. Okay. So this is what one, you can say, issue, or one, you can say, major you call breakthrough they have done. But really this is not a breakthrough, because so 4 parameter, how you will bring it to 6 to 4? That is the biggest question. So the next slide it would address, but right now you can understand that the Danawit-Hartenberg brought a parameter which is what we are going to call kinematic parameter. These are only 4. So how they made it 4, that is we are going to discuss further. But now we will actually like see further set. So what this Danawit and Hartenberg brought, so they brought one additional thing. They said there is a 2 set of transformation we can do. Although you have 4 parameter, but there are 2 set of transformation we can do. So one set would be associated with the joint to joint. Okay. So the other set is actually like link to link. The link to link, what we call, it is actually like associated with the joint, because the link to link is connected with one particular joint. For example, I assume this, the pen is one joint. My you can say 2 arms are actually like connected in this. So now I can see that these 2 arms actually like relatively you can say rotate or translate about this, you can say, pin or pen, right? In the sense, you can see that the transformation associated with you can say 2 link information can be represented with one, you can say, set. That is what we call joint parameters. Okay. So whereas you call this is a link, okay, this link minimum will be connecting 2 bodies, right? So in the sense, this body would be attached with ground or one body, and the you can say the link would be progressing with another, you can say, set of bodies. In the sense, if you take any random link out of the manipulator, you can see that would be at least associated with 2 other bodies, right? So in the sense, you can see that what this particular link is defining. So these 2 bodies are actually like associated in 2 of the, you call, joints. So now this particular link would be associated with the link parameters. So in the sense, the joint to joint information I can write, or I can deliver with the help of one simple set called link parameter set. So this is what the Danavitt-Artenberg have done. So further what they have done, there are some simplification they have done. So that is what we are going to see in this particular, you can say, lecture. So what they have done, they said that one of the biggest issue what they have mentioned, that any body which I am calling with respect to Danavitt-Artenberg, so that body called binary link. So in the sense that body can be attached only with two other bodies. It can be ground and one progressing body, or random link you take. You can see this is I call link k minus 1. So this would be associated with link k minus 2 and link k. Okay, if I take link k, so this link k would be associated with the link k minus 1 and link k plus 1. So in the sense you can see, if I take this is the body, so this body is associated with, you call, two joins. So in the sense this is I call k minus 1 link. So this is actually like k minus 2 and k link. So this is what we call binary link. So binary link in the sense I have two joins only associated. So this is what one you call bigger assumption they made. So the second assumption what they said, so each joint, or you can say each constraint, has only 1 degree of freedom. In the sense it will allow only one motion. So for example, if I take this as actually like one, you can say this is one link and this is another link. So this particular joint, okay, will actually like allow only translation, or actually like it allow only rotation. Okay, in that sense. So in the sense you can see that the two body associated with one joint, the joint will allow either translation about its axis or rotate about its axis. That's all. So in the sense it's what we call 1 degree of freedom joint. Okay, so this is the second assumption they made. So what is the third assumption? That is actually like straightforward. So they said that the coordinate frame, whatever you are taking it, which is what we call Cartesian coordinate, so you have to follow the right hand rule. In the sense if you associate with the two axes, so the third axis automatically will come. And third thing what they have, like the fourth thing what they have done, so the right hand rule used for the positive rotation. In the sense you put your thumb actually like along with your joint direction, positive direction, how your fingers are coming outside, that is what you call positive rotation. So these are the assumptions they made. If you see this assumption, then the link would be having only two joint. And if you take the second assumption, each joint would be having only 1 degree of freedom. Either it is actually like translate, or actually like it allow the rotation. Okay. So this is I call the link 1 and 2. This is a joint. So this joint actually like allowing the rotation, or you can see this is one link and this is another link. These two links would be actually like moving in a offset plane. That's all. In the sense you can see that you are reducing the total, all the joints, bringing to only two subset. So what are the two subset? So either the joint supposed to be a rotary joint or translation joint. That's all. The translation joint we call prismatic because it is going to make a prism along with the axis of, you can say, translation. So that is what we are actually like calling it. So these assumptions you got it right. Now we will go further. So what then they said, since we have already restricted these all the cases, right? So in the sense you have only binary link and you have only you can say 1 degrees of freedom joints, then you can definitely, you can see that there are some constraints or there are some informations are actually like inherent. So in that sense you can actually like bring only 4 kinematic parameters. These 4 kinematic parameters also what we are going to do, or what Danavitt-Artenberg has done. So they are actually like further divided into two subset. So 2 of the parameter would be associating with the joints, in the sense the link information. So the 2 other parameter is actually like associated with 2 links. So in the sense it is a joint parameter. That is what actually like they have done. In the sense you can say the information about 2 adjacent link, that would be given in the joint parameter. The information about 2 adjacent joints would be giving the link parameters. That is what they have done. Okay. So the link parameter is actually like representing the information between 2 consecutive joints, and the joint parameter is actually like the information between 2 consecutive links. Okay. So this is what the bigger you call assumption. So these 3 assumptions, based on that what we are actually like going to do, these 2 subsets we are going to derive. Okay. So now we can see how further it is going to do. So in that sense, what happened, there are only two axes would be referred because we are already using the right hand rule. The third axis information can be easily obtained, right? So then there is a choice of two axes, right? So you have X, you have Y and Z. And what else you have? So you have actually like joint parameter and the link parameter. Okay. So the link parameter would be two parameter and joint parameters are actually two joint parameters. So but you can see that there are two parameter set, but there are three axis options. So then you can see that the links, how it is arranged one to another. So this is one link which I call actually like ground. So the another link is actually like attached like this. The third link is attached like this. So you can see that the link is actually like progressing in the direction of vertical axis, right? So in the sense you can see that I want to give the information between these two. I can see this is the joint, right? So now this joint is actually like how it is actually like in the, you can say moving across the vertical direction. So in the sense what you can easily fix it. So the joint information I can put it in the Z axis because the joint information, or you can say the link to link relation is giving with the joint. So this is actually like associated one body, another body, like that you are actually like progressing with the vertical movement, right? In the sense the joint parameter associated with Z axis. Then you can see that this is one joint and this is another joint, right? So how this joint to joint information is going across? This is going across the, you can say longitudinal direction. So in the sense it is actually like going our screen left to right hand. So which is usually what we consider, it is actually like considered as X axis, right? In the sense the link parameters what we can associate with X. So then one can ask, sir, why can't we put it in Y axis? Yeah, you can put it, but the Danavitt-Hartenberg put, so X for link, Y, Z for you call joint and Y for none. So in the sense, two parameter would be associated with Z axis, two parameter would be associated with the X. So in the sense, the Y axis parameter is inherent, there is no further information is required. That is what the Danavitt-Hartenberg have done. So in the sense, you can see that these are, we are talking. So one is actually like joint parameter. The joint parameter is actually like nothing but two things will come. So one is actually like how one joint is actually like defining one link to another link. So in the sense this joint is actually like relating two consecutive links. So how this link is arranged, so how far and how orient. So in the sense you can see that any parameter what you call joint or link, it would be relative position and orientation information. That's all. Now it is a joint parameter, it would be two successive links. If it is a link parameter, relative position and orientation of two successive joints. That's all. So this is what we are actually like going to talk. So you can see the link parameter is actually like relative position and orientation of two successive joints. So just to give a very simple aspect. So I'm actually like taking it one simple body. Okay. So now you can see that this is one joint. I'm actually like taking it as a three-dimensional body so that it is easy for you. So now I'm seeing that this is a three-dimensional body. So you can see this is three-dimensional body. The first joint I actually like fix it like this. Okay. Or I'll just make it a different color. So the first joint I'm actually like putting it this way. Okay. It is easy. But the second joint I'm actually like putting a projection. Okay. I'm putting like this. So now you can see that this is joint 1 and this is joint 2. This joint 1 and joint 2 is actually like what happened. There is a, I call this is the frame 1 and this is the frame 2. You can see that this is actually like distance apart and as well as the orientation apart. So these are the two information which I call the link parameter because this is giving information about joint 1 and joint 2. The same way you can see this is one link and this is another link. Okay. So now this is actually like going like this and this is actually like going here. So now I'm actually like seeing here and that too like I'm seeing in a top view as well. Okay. So this is link 1 and this is link 2 and this is a joint. So what one can see, so this link 1 and link 2 is actually like you can see that the frame is actually like distance apart. Okay. And second thing is, you can see this frame and this frame is actually like orient apart. So in the sense, the relative position and orientation of these two successive links can be represented as one set that is related with this particular joint. That's what it is called joint parameter. We'll see little more detail. Okay. So for that, what we are actually like talking about. So we are actually saying that the joint parameter always associated with z axis. Okay. And the link parameter is always associated with x axis. So obviously we are actually like leaving the y axis. But what else is there? So you can see that the xi minus 1 frame, because we are talking about you can say several axes. So I am saying that we are taking a random link called link k or link k minus 1, then that would be associated with I minus 1 frame and ith frame. Okay. So now these two are having two axis set, right? So xi minus 1, yi minus 1, zi minus 1 as the one set of you call axis. The other set would be xi, yi and zi. So now the xi always supposed to intersect. Okay. So then you can see that you can actually like take zi and zi minus 1, and where they intersect, that point you can take as the frame, and the axis you can actually like see how it goes. Then you can actually like say that is what the xi minus 1 frame. So in the sense, the perpendicularity. So the second thing is the frame not necessarily supposed to be on the link. For example, I have a link like this. Okay. And there is a joint which is actually like going here and here. So what I can see that the common normal can go here, right? So I can even fix my frame here. So that is what the idea here. So now we'll go further. And only 4 parameters are enough as per the Danavitt-Artenberg. That is what we are actually like discussing, in the sense there is no need of 6, we can have it 4. But inherently the 2 other parameters are actually like fused with certain assumptions, right? That you can all agree. So now in order to discuss about the link parameter, I have taken a random link. You can take this as you call the random link. So you can see this is what you call the first axis, is that I minus 1 axis, and this is actually like you can see it is coming towards me. So this is the way it is look like. So this is the random link k minus 1, and this is k minus 1 axis, and this is kth axis. So now you can see that this is what I am just showing it. Okay. So now you can see that this is what the link. So now this link is having what happened. There is a transformation, in the sense translation, and as well as these two joints are actually like distance and orientation apart. This is actually like perpendicular to the ground, and this is actually like pointing towards me. So now you can see that there is a angle between these two, and similarly you can see that there is a distance apart, right? So this is what we are trying to see. The first thing what you have to do, you have to make the common normal between zi minus 1 and zi. So now that is the common normal supposed to be your, you can say, axis of your rotation, in the sense xi minus 1. You fix it that, and now you rotate about xi minus 1 in order to make zi minus 1 parallel to zi. So in the sense, I am taking, this is zi minus 1, and this is actually like my zi. So now I made the common normal. Okay. So now what happened, this is what my axis, which is I call xi minus 1. So now I am actually like rotating about this. So what happened? So this much angle it would actually like rotate. So this angle I call alpha, and this is actually like rotated about I minus 1 frame. This is alpha I minus 1. So what that means? So the link was like this. Okay, it is parallel, but you have actually like twisted. So now you are actually like making back. So that's what it is called, twist angle. Okay. So because it is actually like the link is twisted between two axes. So supposed to be parallel, but it is actually like twisted. So that's why the angle between zi minus 1 and zi with respect to or along or about x minus 1, this angle you call twist angle. So now the positive rotation is about, you can see xi minus 1, you put your thumb finger, how it is coming outward, that is what the positive. In the same, the alpha xi minus 1, alpha I minus 1 is the positive angle. Okay. So now you can see that what you made it. So you made it parallel. So in the sense, zi minus 1 is parallel to zi. Okay. I put star. So now what you can see, this is actually like some distance apart. So now what I am trying to do, so I am actually like, this is what the case, I make it parallel. So this is one operation I did. So now I am actually like moving forward, right? So the distance apart. So along xi minus 1, whatever the distance, that is nothing but the link length. So now you can see if I fix it this is the link length. So in the sense the link length cannot be negative. Why? Because link length is a geometric parameter that cannot be negative. What it can be maximum? It can be 0. In the sense both axes are coincide at one point, but it is an angle apart. Okay, like this. Okay, so that can be done. So in the sense you can see the a minus 1 is actually equal to 0 or positive. That is what you're supposed to do. So I'm giving the definition little more, you can say based on understanding, clarity is given. So the first one is link twist angle. So the link twist angle I'm writing as alpha I minus 1, in the sense we are rotating about I minus 1 frame. So what is this? The angle between zi minus 1 and zi about xi minus 1. Okay, so that is what the case, what you call link twist angle. So the second thing is link length. The link length is actually like the distance, or you can say distance along xi minus 1 from I minus 1 frame to ith frame, or you can call zi minus 1 to zi. Okay, that is what the case. It is supposed to be a perpendicular distance. So it is actually like zi minus 1 to zi, the distance along xi minus 1. So these are the two things. And as per our understanding, what we said, the joint parameter is actually like defining, you can say, relation between two links. But the link parameters are actually like defining the, you can say, the relation between two joints. So once the joints are decided, then what you can see, the link is actually like fixed. So in the sense, this is what you fix as two joint axes, this link length and the link twist is fixed. In the sense, these two parameters are geometrical parameters. So in the sense, these two are fixed. Okay. Why we are actually like fixing? Because we always assume that the, you can say, joint is actually like degree of freedom represented. So in the sense, the motion between two bodies are actually like possible only along the joint axis. That too, like what we restricted, it is 1 degree of freedom joint. In the sense that you can say link to link, the distance can actually like change, which is you call translation, or the orientation can rotate. So in the sense, rotation. So in that sense, these two parameters are supposed to be fixed. If you are assume that these are variable, then this is what your zi axis. Okay, so not xi minus 1. That's supposed to be very clear. So now the next case, so you can see this. Okay, so now I am actually like taking it. So these two are, you can see, one link and this is another link and this is the joint. So now you can see that these two links are actually like oriented apart and as well as distance apart. So this distance we can simply see, this is one plane and this is another plane. So it is actually like the distance. So which is you can call joint distance, or you can say it's an offset, right? It's an offset distance. So what you can see about this axis, these two are actually like rotated apart, right? So this is what you call joint angle. So if you are saying this is a rotary joint, this is a variable. If you are seeing a translation joint, this is a variable. That's all. So now what you are actually like seeing, this is link I minus 1, link I plus 1 and this is link I. Or you can see this is link I minus 1 and this is link I. Then this is a joint I. The joint I is giving the relation between, you can say, a link I minus 1 to link I. So in the sense, what you have to see as the representation, or what's supposed to be the reference is this axis. Already you know, like this is actually like joint axis. The joint axis is supposed to be associated with your z axis. So zi is already known. So this is your xi and this is your xi minus 1. So the angle between these two, about this angle called joint angle, and the distance between you can say xi minus 1 to xi, where along you call zi, what you call joint distance. So that is what we are actually like defining. You can see that this is the frame to frame, this distance is what you call joint distance, and the angle between these two are actually like joint angle. And again we will use the right hand rule. So you can see this is the case and this is the positive rotation, then the theta I is positive. Okay, So now that is the case. So the joint angle is nothing but the angle between xi minus 1 and xi about zi. So that is what you call, you can say joint angle, and this angle is represented with the ith frame reference. So that's why it is called theta I. Okay. Earlier case what we have seen, it is I minus 1 frame, that is alpha I minus 1, but here actually like it is theta I. Okay. So then the next one is joint distance, where the joint distance is actually distance between xi minus 1 axis to xi axis along zi. That is what you call joint distance. Okay. So this is what the joint distance along zi. Okay. So now this joint distance can be negative, but the link length cannot be negative. Okay. And further what you can see along, you can say about, right? So with respect to these two parameters, as per the Danavitt-Artenberg approach, so either one of them supposed to be variable, the other one is fixed. Why it is so? Because we assume that so every joint is actually like having 1 degree of freedom. So either it would allow translate along the axis or rotate about the axis. In the sense, either one of these are actually like constant, one is actually like variable. That is what we are actually like telling here. So in the sense, you can see that in these two parameters, any one of them is variable and the other one is constant. The joint distance, I already said, this can be called as offset distance because this is one plane and this is another plane. It is actually, the plane is offset, right? That's what it is called, offset distance. So now we will actually like see if it is a prismatic or translation joint, the joint distance is variable and the joint angle is constant. In a rotary joint, the joint angle is actually like variable because you are putting a rotary motor, and the distance between one link to another link is fixed. In the sense, this is your motor case and this is actually like your shaft length and this is another body. Okay. So for example, you are taking, this is your motor and you are actually like attached with the link. So now this distance is actually like fixed. Okay. Now this is actually like rotation angle. So theta I is variable and di is constant. Okay. So this is what we are actually like defining it. So I hope you understood, and next class we will actually like go further as a recap, and then we will move to the Danavitt-Artenberg notation. In the sense, we will come back with how one you can say frame to another frame, how we can use these 4 parameters to come up with the information what you call transformation matrix. The transformation matrix we hereafter called arm matrix. So that we will see in the next lecture. But now what we have actually like gone through, we have actually like gone through one of the simple aspect. So what that means? So we have actually like made it what is kinematic parameter and how many kinematic parameter and what are they. These all we have seen in this particular short lecture. So again I am just recapping. So the Danavitt-Artenberg did not do anything. So they have actually like assumed actually like several of them. So one assumption is that so every link would be having only 2 joints. So in the sense it's a binary link, and every joint would be allowing only 1 degree of freedom. In the sense it can be either translation or rotation. And third thing is we are actually like using right hand rule. And fourth thing is actually like we are actually like bringing it with only 4 parameters. So 2 of them are actually like relating with you can say 2 adjacent links, which is you call joint parameter, and 2 other parameter we call link parameter, which is going to give the relation between 2 adjacent joints. So now this 2 parameter would be simply relation or relative position and orientation. So now this is the relative position and orientation. We have to bring the axis. So now you have 3 axis system, but what Danavitt-Artenberg has made, so the joint parameter would be associated with the z axis, because this is actually like link to link as assigned, in the sense it is actually like vertically piled up, so that easily you can say it's a vertical axis. So we usually conventionally go vertical axis as z axis. So in the sense, the link to link information about joint can be represented with respect to z axis. So then there are 2 parameter. So one is joint angle. So in the sense how one link to another link is actually like orient apart. So now the link parameter is associated with x axis. Why? Because we always assume that the link is binary link, in the sense 2 joints are there. So these 2 joints are actually like how associated, whether it is twisted or it is actually like parallel, or it is distance apart, or you can say coincide. So in the sense the relative or you can say relation between two joints in terms of relative position and orientation given with the link parameters. Okay, so now you got, I hope, some clarity on kinematic parameter. The kinematic parameter simply hereafter we call DH parameter. There are 4 parameters. So general kinematic parameters are 6, which is 3 translation and 3 orientation, but the DH parameters are 4. So 2 kinematic like a 2 joint parameter and 2, you can say, link parameter. In that 2 link parameters are link twist and link length are constant, and out of 2 joint parameter where joint angle and joint distance, either one of them are actually like constant, the other one is variable. If it is a rotary joint, the joint angle is variable. If it is a translation joint or prismatic joint, the joint distance is variable. So with that, I'm actually like closing this particular session, and I will come back with the you can say arm matrix or Danavitt-Artenberg representation in the next lecture. With that, I'm saying thank you here, and we'll meet in the next lecture. Thank you. Bye.